Welcome back. The demo that I'm going to do now is also a good experiment that we do in class. It's called vector addition and subtraction using our force tables and then also doing some calculations and then seeing if we get the same results. So this force table is basically we can put pulleys on the four sides. We have 4 pulleys. And then I can kind of rotate this. On top of the force table is written the angles. I can rotate them so that the 0 angle is facing this way. So from your point of view, this will be 0. Towards me will be 90 degrees. This one will be 180. And then this one will be 270. Right? So then I can say, let's add 3 vectors to each other and see what the sum of those 3 vectors is. So it's going to be D is equal to A plus B plus C. So I can make the angle and the magnitude of these vectors anything I like. So let's call this vector A. I'm going to put vector A at 65 degrees. And then the hanger already has a mass of 50 grams. So I have to count the mass of the hanger. So I'm going to put 100 grams on top of the 50. I'm going to put 100 grams on top of the 50. So that's 150. Okay. So my vector A is going to have a magnitude of 150. The angle of vector A is going to be 65 degrees. So by just looking at it from the top, you can see the angle of the string is a 65 degrees. Then I'm going to make this anything else that I like. Let's say 158 degrees, 158, right? And then I can put any weight there that I like. I'll put 50 grams on top of that. So then my vector B is going to be, the hanger was already 50 and I put 50 there, so that was 100. And then the angle of vector B was 158 degrees. 158. Then I can have a vector C. Then I can make my vector C anything I like for that to be. Okay, so let's make this one 113. Then I'm going to ask, what is the sum of these 3 vectors, right? So the way that the force table works is that when you add these 3 vectors, it tends to pull everything to this side, right? So then I'm going to have to adjust the angle of the 4th pulley and put some weights on it until the system is in equilibrium. So this one will give me the opposite to the sum of the 3 vectors. We call that the equilibrant vector. It's the vector that cancels the sum of all these 3. Right? So then once I find what this vector is, I can just take the opposite of that, and that gives me the sum of the 3 vectors, right? So then if I take the middle screw out, right? If I take the middle screw out, so of course you're going to see everything will tend to go this direction, right? So then I'm going to have to put some weights there. So I can kind of first start off by putting a random weight, let's say 100 grams, right? Then take the middle screw out. And then kind of play with the direction here. So what I want is at the end, I want the middle screw to be at the center of the table. I want the middle screw to be centered in the middle. You see? So this screw, this washer needs to be where the screw originally was. It needs to be centered right there. So right now it's still off to the side, you see? So then I'm going to have to adjust the angle. Okay. So then I'm going to have to put some more weight on it. You see? But now it came over too much. The screw is here. You see? You want it to be there. So I'm going to have to adjust the angle a little bit. Take out some weight. Take out some weight. You see? So maybe now add a little bit less. Okay? Okay, so that looks kind of like centered. We can kind of displace it from center, and if it keeps going to the center, that's a good sign. You go like that. I could put the screw in. It seems to be, I'm in the ballpark. So then my vector here is 321.5. Okay, the angle of the vector D, we got 321.5. That's this one, right? But remember, the this gives you the opposite to the vector D, right? This gives you the vector that makes the system in equilibrium. So we have to subtract 180 from this. So 180 subtracted from the 321.5, that gives you theta D experimental is 141.5 degrees, right? Then in order to get the magnitude of the vector D experimental, we calculate, we measure how much mass we have here. We have here 100, I have 100 and the hanger is 50, and then 20 grams, that's going to be 170 grams. 170 grams. Now let's calculate what the theoretical vector D is, right? So in order to do that, we have to break the vectors into x component. dx is equal to ax plus bx plus cx, right? So we have here ax is 150 cosine 65, and then bx is 100 cosine 158, and then cx is 120 cosine 213, right? When we compute that, dy is equal to 150 sine of 65 plus 100 sine of 158 plus 120 sine of 213, and that one we get 1. Then the magnitude of the vector D theoretical is going to be square root of 130 squared plus 108.1 squared, right? So then you get this. I didn't even know my theoretical result, and my experimental result was less than 1 gram off from the experimental, right? So that my percent error is going to be very good result here. 100% times 170 minus 169.1 divided by 169.1. So even though there were all these sources of error, I didn't level the table, there's friction in the pulleys, I got less than 1% error by simply trial and error, finding out how much mass is required to center the pin, right? So then how about the angle? Let's do the angle. We can say here, let's analyze the quadrant that the vector D is in. For the angle, you have to analyze the quadrant of the vector D a bit. dx is negative, which means it's to the left, negative 130. dy is positive, so that's 108. Okay? When you put dy to the tip of dx, you get the vector D is in the second quadrant. So let's calculate the angle by taking dy over dx, right? Tangent of the angle, dy is going to be 108.1. And then dx is going to be 130, right? So right now, forget that dx is negative. Just take its absolute value. So calculate the angle here. So when you take the ratio of 108.1 to 130, you get 0.83. And then you take the inverse tangent of that to calculate the angle. Theta is the inverse tangent of 108.1 over 130. The answer comes out 39.7 degrees. 39.7 degrees. Okay? Well, then you say, since the vector D is in the second quadrant, its true angle is measured from the positive x-axis, right? So we subtract 39.7 from 180, right? You subtract that from 180, you get 140.3. So the true angle of the vector D is 140.3 degrees as measured from the x-axis. Then you compare that to 141.5. We are a little bit more than 1 degree off. So very good result. So my percent error is going to be what? My percent error is going to be 100% times 141.5 minus 140.3 divided by 180. The reason I divide by 180 is because the most I can be off by from an angle that I'm supposed to be getting, I can be off by 180. If I'm 180 degrees off, I'm in the opposite direction and I am 100% error, right? So now let's compute the error. We get here 0.67% error. So I am very good satisfied with this result, right? 0.5%, 0.6%, even though there's friction in the pulleys and I did not level the table and I did, I was just by myself. I didn't have a partner check with me, but the result is excellent, right? Now we can practice vector subtraction, right? Instead of vector D being a plus b plus c. Let's say vector d was a plus b minus c. So the last vector was subtracted. How do we do the theoretical result? So then we subtract this, then we're going to do the force table, right? So what result do we get now? We get here 71.3. So this one completely changes. 71.3. Now let's do the subtraction for the sine. We get 238.8. Okay? So which quadrant is the vector d in now? So the vector d is going to be in the first quadrant. Right? So then it's going to be like this. Right? So 71.3 is this side, 71.3, and then dy is going to be 238.8. So now, to compute the magnitude of the vector d, I say 71.3 squared plus 238.8 squared. Right? Okay. And then the tangent of the angle is going to be, then you do dy 238.8 over dx, right? And then you take the inverse tangent of that. When you divide these two, you're going to get an answer like 3.5. Then you're going to take the tangent inverse of that. You're going to get 73.4 degrees. This time, because the vector d is in the first quadrant, I don't have to touch it. I don't have to add 180 to it. I don't have to subtract it from 180 or subtract it from 360. If the vector d is in the first quadrant, you keep the angle as is. Right? So then my answer is going to be now 73.4. 73.4 degrees. Okay, so now let's do the experimental. Let's assume I don't know the answer. Right? So how do I do vector subtraction? This is the vector A, this is the vector B, this is the vector C, but I'm trying to subtract vector C. So what I'm going to do, to subtract vector C, it's like adding, it's like doing this. So when you do D is equal to A plus B plus negative C, right? So subtracting a vector is like adding the opposite of the vector. So how do I make opposite of the vector? Well, this angle vector C was 213. Opposite of the vector C would be what? 213. Then I subtract 180 from there, I get 33. So I need a vector opposite to the direction of vector C, right? And I need it to be the same weight as vector C. So what I could do is I could take the weight of this, replace this with this, put this weight on that vector, rotate it until this one is showing 33 degrees. Okay? So now this becomes A, this becomes B, this one is negative C. Now I play around with this one. I play around with that until I get the pin centered. Okay, so let's do that one now. Okay, we're going to get like this. Something like that. Maybe put some 100 grams on it. Let's see what happens. Grams. Take the screw out. And it's going way, way to that side. So I need maybe another 100. Okay. So then the screw is in the right. It's coming this way, but it's to the right. You see here? This is the center screw. And the middle washer is to the right of that. So now play around with the angle. Bring the angle like this. Take the screw out. Okay, play around with the angle. Okay. So now this seems to be centered. I don't even think I need more weight. If I add any more weight, it's going to come to me too much. You see? So if I displace it from equilibrium, it goes back to the center. I can put the screw in really nice, centered, adjust the angle. Right there, pretty nice. Okay, so then, let's say I didn't know the answer. Okay, so then I just basically base my results off of this. This is A, B, negative C. So whatever answer this is, the vector D is opposite of that. This always gives you opposite of the vector D, right? So right now I have showing 253, okay? 253 degrees. So the angle of the vector D experimental, 253 degrees. Then I subtract 180 from that. So this is 253, 180. So then that's going to be 73 degrees. Okay? This one is 73.4 degrees, the theoretical. So such a small error, right? For a lab that has friction like this, so has a lot of uncertainties. Such a great result. Okay? How about the magnitude? Well, let's weigh this, how much we have here. This is going to be 100, 200. I didn't need any more weight except 200 and then the hanger itself. So that's 250. Okay? So the magnitude of the vector D experimental, 250 grams, right? And the theoretical result was 249.2. Okay, so that my percent error is going to be 2% error. So again, very, very low error. So this is a really excellent result. So now you can see how you can use the force table to do vector addition and vector subtraction. The force table is a great tool both in a physics class and in a math class to teach trig. So this could be a great way for students to really, really practice adding their vectors, doing their sines, doing their cosines, practicing their tangents, right? Put any random weights, play around with the pulleys, see what result you expect to get, then do the math and see if you get the same result as what the force table is predicting. So it's a great learning tool for both physics and for vector additions, for trig, and for any kind of math class involving trig. Okay? Thank you very much.